Hello.
Chetana.
Hello, sir. Can you hear me, sir?
Yeah, we can.
Okay, sir. Shall we start?
Yeah, please.
Yes, sir. Good afternoon, everyone. So this is Chetana HP, Assistant Professor, Civil Engineering Department, VKIT. I welcome you all for the second session of first day of our 5-day webinar. This session will be on pre-engineered buildings, design and construction, presented from Mr. S. Chanda, Senior Manager, Civil and Structural. So can you hear me?
Yeah, please proceed.
Okay, sir. So Mr. S. Chanda obtained his bachelor's degree in civil engineering from erstwhile Bengal Engineering College, Shibpur. Before joining INSDAG in 2004, he worked for a few consulting and contracting companies and was in charge of pre-engineered buildings division. Presently, he is working as Senior Manager, Civil and Structural in INSDAG. He has hands-on experience in PEB Designs, drawings and construction. He also holds a postgraduate diploma in General Management from XLRI Jamshedpur. So now I would like to request Dr. Shashkumar Sir, Head of Civil Department, to welcome the speaker.
Hello, Chetana.
Hi, sir. Hello.
Yeah.
Yes, sir. I just asked you to welcome the speakers.
Yeah. Sorry, there was an interruption. Sir, on behalf of staff and students of Civil Engineering Department VKIT, I would like to welcome Dr. Chanda for this webinar. I think we are very grateful to have you here, sir, and we are very keen to listen to the prestigious prefabricated structures design and construction. And thank you for accepting our invitation and being a part of this webinar, sir. Thank you so much.
Hello. Sir, hello.
Yeah. Chetana, you can start.
Shiladitya, you can start now.
Yes, sir. Over to Dr. Chanda.
Hello.
Yeah.
Am I audible?
Yes, sir.
Am I audible?
Shiladitya, now you can start presentation.
Yes, sir. Yes, sir.
All other. So I request all the others to please mute the.
Mute. Am I audible?
Shiladitya,
Yes, sir.
loudly.
Sir, I am audible?
Sir, you are,
Yes.
sir. You are audible, sir.
Thank you, Mr. Samantha, and thank you, sir, madam, for giving me an opportunity to speak over here. So, our topic today is pre-engineered building, design and construction, right? So, with your permission, so let me start the presentation, and I am sharing my screen now. Is it visible? Hello?
No, sir, it is not.
The screen is not visible, right?
Not visible, sir.
Now is it visible, sir?
Yeah. Yes, sir. Yes, sir.
Okay.
It's visible, sir.
Okay, fine. So let me move on. So the topic today is pre-engineered buildings, design and construction. Now this pre-engineered building concept is not new, as you most of you are already aware of. This particular subject is in India for say last 20 to 25 years. Initially, it was in a very bad shape, and we used to copy the foreign contractors and all. They were few foreign contractors. They actually brought this concept here in India, and after that, right now, say 20 to 25 years down the line, it is a very established industry right now. Supply chain is very stabilized, and I believe, today's audience is most of them are students. So I have modeled this particular presentation that way only, so that they could appreciate and they could link whatever they have learned in their classroom. So first of all, we should try to understand what is pre-engineered building actually. Why it is called pre-engineered? Pre-engineered building is called, if you say compared with pre-engineered building with say prefabricated structure, everything is prefabricated, and to some extent everything is pre-engineered also, because whenever we say prefabricated, we used to say engineer beforehand, we used to draw beforehand, and then only we move to construct, the workshop floor, and then construct or fabricate, and then we move the whole thing to site and we erect. But in this thing, that this is pre-engineered building, one marvelous thing is that it is a little different, because this is the pre-engineered, because it is predetermined assembly of structural members. That is, whatever students learn from their classroom, everything will be applied over here. Everywhere it is being engineered so that we achieve an economy. That is, so if we move on, you can see that how the economy is achieved, how the aesthetics is achieved. So these are some advantages. So first of all, we will go for normal thing. We will learn the advantages, we will learn the application, and then we will move on the design and construction. So if we go through this, most of the advantages are quite well known, and it is established also, and students, everyone knows that. So the faster construction, yes, definitely steel allows for faster construction, as we all know. But within the steel industry or within the steel construction also, this particular PEB construction techniques allow for even faster construction, because everything is predetermined. And everything is very much standardized and modular in shape. So that particular thing allows for faster construction. Now, the point 2 is high strength to weight ratio. That is normal for any structural steel construction. This will be achieved, because steel's property is itself like that. Lower cost. Obviously, when we say the faster construction, it saves us time. It saves labor cost also. So we can monetize the project earlier. Those things are, when we say construction stage. Now the particular PEB thing, the shape or the geometry is so optimized that there also we achieve economy compared to other steel structures. Right? And as we move on, you can see how we achieve economy, how, every engineering aspects are being maintained over here, so that, the total shape is optimized, wastage is minimized, and that way we can also have the foundation cost lower also. For say, when you talk about large span, yes, in PEB does allow us for going for a very large span, up to 80 meter, 90 meter is possible over here. You can see the airport hangars. Airport hangars are not PEB, but nowadays some contractors are going for PEB also. Expandability, yes, this particular construction technique allows for expandability in say longitudinal direction as well as horizontal direction. You will see when we talk about, say, the frame geometry and all, overall structure, we will explain how this is expandable. Quality control. I mean, when everything is, predetermined, drawings are made beforehand, fabrications are done in soft floor, you can expect the quality control will be of the superior quality and a superior level. So the quality control is achieved by issuing this predetermined assembly. Architectural versatility. I mean, you can think of any large span structure, PEB can be applicable. And that is how we achieve this architectural beauty. Energy efficiency, nowadays we are having a lot of, insulated panels and also, and you can see, if you have seen the architecture, this PEB structure, you will see on the top, a lot of monitors are being installed so that the air circulation is established, and that is how the interior atmosphere is being maintained. So this particular type of structure is very much energy efficient. Now, if you say these application areas, you will find here is a list. You will find all the aspects of, say, structural construction. PEB can be applied, and nowadays it is a fact that PEB has taken over a lot of space. Conventional structure, most of you will not see.
Sir, excuse me, just a minute.
Hello?
Sir, just a minute. I have one announcement. Those who are joining in Google Meet, can you please join using the YouTube link which is available in the group? Because it is disturbing a lot. The other people are unable to listen to the lecture. Can you please join using the YouTube link instead of joining in this Google Meet? Please, it is disturbing a lot. Sir, you can continue, sir.
Can I proceed, sir?
Yes, sir. Please, sir.
Hello.
Yes, please, sir. Please, sir.
Okay. Thank you. So these are the application areas, as I was saying, that you will not find any areas in which PEBs are not applicable. Nowadays, PEBs are applicable almost everywhere, and you will see the conventional structures are getting obsolete by day. Only in few, say, plants and all, you can see few conventional structure. Otherwise, for most of the cases, PEB is taking over the conventional structure in a big way, actually. So now let's move on to the content, actually, the subject of this particular presentation. That is, the subject of this presentation was pre-engineered building, design and construction, right? So, throughout this presentation, we will touch upon these issues. Under design issues, we'll first see how this frame can be optimized, as I said. Then the framing systems will go after that. We'll go through the component descriptions. What are the components in a typical PEB? Then we would slowly move into the design parts. That is, what are the codes to be in conformity, we should design in conformity with. And then few loads, what are the loads to be considered for designing a typical PEB building. Then we will see the deflection limits as per code. Then few important conditions, that is support condition, typical connections, how this pre-engineered concept is being applied over here. Those things we will see in a structured manner. Support condition we will see, then we will see the connections, purlin and guards. There you will find another marvelous example of, the whatever you have learned in your class. Okay, then if start bracing, then few issues with stat modeling, because after all we will be designing this particular structure in stat, and then few welding issues. And in the construction side, we will look into these foundation and anchor bolts part, storage part, installation of breakers or flange braces, and sheeting, and few issues related to sheetings and claddings. But what is most important, students, here that we have talked about the advantages of pre-engineered buildings, and we have seen, we have already told that pre-engineered building, gives one aesthetic beauty, right? But another aesthetics is there in the pre-engineered building, and that is from the engineering side. And that is not listed over the previous slide. That is, the aesthetic lies here. In the pre-engineered building, you can apply almost everything you have learned in your field. In the last 4 years, whatever civil engineering you have learned, that you can apply almost everything over here. That is another beauty over here that is not listed, of course, but you will try to appreciate that as we move forward. So first one is the frame optimization. You can see here how we, in the pre-engineered building, how we can optimize the frame. You can see in a typical one span, simple span structure portal, under dead load and live load, you can see, just let me enable the pointer over here. So you can see okay, if you make this support pinned over here, that is shown over here, pinned, then this is the typical bending moment diagram you will achieve. And our frame follows exactly like that. Here, as it is a pinned base, you will have 0 moment over here, and we will have, you can see, a minimum section over here. It is basically an I section, where flange, these are flanges, and this is wave. These are welded together. Right. Here we are having the maximum moment, and you can see here the depth of the section is maximum. Here also, this is called eve, right? So here also, from the bending moment diagram, you can see you will have bending moment, maximum bending moment occurs over here. So this particular thing is achieved over here. This is the point of inflection. It is basically, and we are having minimum I section, so where flange, these are flanges, and our frame is moving like that together. Here we are having the maximum moment, and you can see here the depth of the section is, and that is how here also this is called can achieve, right? The minimum. So here also, from the bending moment diagram, you can see you will have aesthetic profile moment, maximum bending moment occurs over here. So, but this particular thing, this we have talked about dead load. This is the point of, and what about the inflection? It is basically, and we are having minimum I section, where flange, these are flanges, and our frame is moving like that over here. And our here we are having the maximum moment, and you can see this is the point of here the depth of the section, and that is how here also this is called can minimum, the minimum. So here also, from the bending moment diagram, you can see you will have aesthetic profile moment, maximum bending moment occurs over here. So, but this particular thing we have talked about. This is the point of, and what about inflection? It is basically, and we are having minimum I section, where flange, these are flanges, our frame is moving like that, and our here we are having the maximum moment, and you can see this is the point of here the depth of the section, and that is how here also this is called can minimum, the minimum. So here also, from the diagram, you can see you will have aesthetic profile moment, maximum bending moment occurs over here. So, but this particular thing we have talked about. These are flanges, our frame is moving like that, and our here we are having the maximum moment, and this is the point of here the depth of the section, and that is how here also this is called can minimum, the minimum. So here also, from the diagram, you can see you will have aesthetic moment occurs over here. So, but this particular thing we have got in the typical pre-engineered building. This is called a typical frame, and in normal parlance, pre-engineered now, as I said, this is expandable, right? So if the structure is, suppose when you design the structure, say client asks a certain age, pre-engineered building. So this is can have a typical particular frame, and in normal parlance, pre-engineered suppose this is a dead end. Now as I said, this is expandable. Suppose this way, the frame will never
If the structure is, suppose when you
further
design the
optimize this
structure,
particular
the client
because
asks
a certain this is the bay.
engineer.
So you
This
can
called
have the data
particular frame, and in normal parlance, engineer suppose this is a dead end. Now, as I said, this is expandable.
This way, the frame will
If
never
the structure is, suppose when you
further
design the
optimize this
structure,
particular
the client
you can have
asks
the doors
certain this is the bay engineer. This can have the data particular frame, and in normal parlance, engineer suppose this is a dead end. Now, as I said, this is expandable. This way, the frame will if the structure is, suppose when you further optimize the particular client asks this is the bay engineer. This can have the data particular frame, and in normal parlance, engineer suppose this is a dead end. Now, as I said, this is expandable. This way, the frame will if the structure is, suppose when you further optimize the particular client asks this is the bay engineer. This can have the data particular frame, and in normal parlance, engineer this is a dead end. Now, as I said, this is expandable. This way, the frame will if the structure is, suppose when you further optimize the particular client asks this is the bay engineer. This can have the data particular frame, and in normal parlance, engineer this is a dead end. Now, as I said, this is expandable. This way, the frame will if the structure is, suppose when you further optimize the particular client asks this is the bay engineer. This can have the data particular frame, and in normal parlance, engineer
primary training
this is a dead end. Now, as I said, this is expandable. This way, the frame will if the structure is, suppose when you further optimize the particular client asks this is the bay engineer. This can have the data particular frame, and in normal parlance, engineer
most of the big time it is 345.
this is a dead end. Now, as I said, this is expandable. This way, the frame will if the structure is, suppose when you further optimize the particular bay engineer.
Again, I said maximum time is of constant length. Some cases where the loads are less, you can have a single section 45. These are the piling and side cuts. Normally, at piling, on side cuts and all, you can have left section as well as this section. But for each cut, you must use sort of special profile. These are the piling. The intersection will learn how to otherwise, we call it on high cut. So the thickness varies from 1.67 to 2.5 and these are generally hot rolled sheet. After that it will form like this, so we call it cold form 6. And there is a intersection the one for such type of component. This is also 340. And sheeting and cladding are also nowadays you can cold form 6 colored coated. And all these things are normally base material. Most of the time they use the 0.44 and this is also 440. Now for bracing. Bracings are typically you have been using stats, so you must have heard that sometimes full subject color as tension. So here also, normally this method engineered building bracing, most of the time we use this method. And we should design those bracings now for bracing, we model the engineered building. We have to assign those subject color. So here also fasteners are most of the time for primary setting, that is rigid frame connections and all. We have to use 8.8 grade force, and for connecting primary Berlin guard, start and all, so we have to use 4.6. We have to assign Bracings are basically used for fasteners connection of with rigid frame structural frame. Structural as well as main primary framing and secondary framing. Like primary rigid frame and secondary framing are Berlin center. So when we attach the sheeting, we need to have something for another secondary layer that is with rigid frame structural frame. Structural normally from Berlin to Berlin. This is required for fixing up the. So when we attach the streams are called, we have already learned about the streams are have consist of another secondary layer. So when this is rigid structural frame, structural and for the reach part of when two main sheetings are connecting together, you will have a top layer that is called streams are called. Now come to code configuration. So as you know, in India, rigid structural frame, primarily use IS 800 2007, and for secondary framing system, the Berlin guard, top layer, IS 801, the current version is 1975, but most of you know that this particular code is going under revision.
Sorry to interrupt again. I think people who are joining in Google Meet, it is really, we are getting lot of trouble from this. Streaming is also not happening properly. Sir is giving such a wonderful lecture and nobody is able to see. Can you please join through YouTube? This is creating really lot of trouble. Such a wonderful webinar, we are unable to listen. Google Meet, YouTube, really it is creating lot of hurdle for us. Kindly cooperate. Please join through YouTube link only. Do not join through this Google Meet. I'm requesting you. There is so many problems for thousands of people. Kindly please. Listen.
From my side also, I can
YouTube. Really creating lot of please join through YouTube link only. Do not join through this Google Meet. There is so many problems for thousands of people.
Sir, can I proceed, sir?
Yes, sir. One second, I will request, sir. YouTubers are really facing lot of trouble, and we are getting message from them. Kindly, because every time, every single second, we are getting one people will go and another people will come. Another people will go, another people will come. Because of internet issues within you, and that is creating lot of trouble to thousands of people. Kindly cooperate. Yes, sir. One second, I will request, sir. YouTubers are really facing lot of trouble, and we are getting message. I request all of you to please log out from this every single second Google Meet. Kindly log out. Another people will come. Another people will go. Another people will come. Because of internet issues within you, and that is creating lot of trouble to. So I want all of you, all the students to please log out. I request all of you to please log out from this Google Meet. Kindly log out. There are another 21 members are there. Please log out. That is creating lot of trouble to. So I want all of you, all the students to please log out. I request all of you 18 member. There are another 21 members. Kindly do not join from this. Sir, one more request, sir.
Sir.
Sir, actually, that bending moment diagram you are showing, no, that slide.
Okay.
Actually, from there onwards, the connection has stopped in the YouTube. Can you please repeat that if you don't mind?
Sir, I don't have any issue, but I presume that was in the beginning of the presentation. So I mean, if you don't have any time issues, I can go to the entire.
Kindly do not join from this. Sir, one more issue. Actually, from there onwards, the connection has stopped in the YouTube. Can you please repeat that if you don't mind? Yes, sir, from here, sir.
Are you referring to this particular slide? But
Yes,
I
sir.
presume
Yes, sir.
that
Yes, sir.
that was in the beginning of the presentation. So
Can I start? All the other all these people, another 9 people are there. Please log out. It is creating lot of trouble in the YouTube. Yes, sir, from here, sir.
Are you referring to this particular slide? But
Yes,
I
sir.
presume
Yes, sir.
that was in the beginning of the presentation.
Please
So
don't join. Again, few people are joining. Kindly don't joining in this Google Meet link. It is creating lot of trouble in the YouTube.
pinned. Okay. So if you make this pinned and under dead load and live load, the typical bending moment diagram will be like this. Fine. This is called if. In the if, you will have maximum bending moment diagram for the column, and at the support you will have zero bending moment diagram, only shear force. And you can see in the actual scenario, so if you make this pinned and under dead load and live load, the typical bending moment diagram will be like this. Fine. This is called if.
We have
the if you will have maximum bending moment diagram
wave depth over here,
the column, and at the
maximum
support
wave
you
depth
will
over
have
here.
zero bending
Flanges
moment
are
diagram,
like
only
this,
shear
shaped
like
like
this.
It is welded.
And you
Basically,
can see in the actual
tapered
scenario, so if you make this pinned and under dead load and live load, the typical bending moment diagram will be like
the
this.
rafter, you will
This is called if.
you have
the if
over here.
you will have
And here
maximum
also
bending
you can
moment
see
diagram
wave depth over here.
the column,
And
and at the
maximum
support
wave
you will have
depth.
zero bending
Flanges
moment
are
diagram,
like
only
this.
shear like this.
It is welded.
And you can see in the actual scenario, so if you make this pinned and under dead load and live load, the typical bending moment diagram will be like this.
The rafter,
This is called if. You have the if
over here.
you will have maximum bending moment diagram
Wave depth over here.
the column, and at the support you will have zero flanges diagram, only shear like this. It is welded. And you can see in the actual scenario, so if you make this pinned and under dead load and live load, the typical bending moment diagram will be like this.
The rafter,
This is called if. You have the if over here. You will have maximum bending moment diagram, wave depth over here, the column, and at the support you will have zero flanges diagram, only shear like this. It is welded. And you can see in the actual scenario, so if you make this pinned and under dead load and live load, the typical bending moment diagram will be like this. The rafter, this is called if. You have the if over here. You will have maximum bending moment I can't hear you right now.
Harish, please reply.
Hello.
Hello, Harish.
Sir, your voice is clear to me.
Yeah. 1 minute. Maybe in that YouTube there is a problem. I think double voice is coming actually. He was telling that in the laptop you have that volume button, sir. Can you reduce the entire voice there or mute that volume button? in the laptop. The right hand side you will have a volume button. Please mute the laptop volume button, sir.
Yes. Fine now, sir. I have reduced a bit. Is it better? I am muted.
Yeah. Now you can proceed, sir.
Hello.
Yeah, please proceed.
Hello.
Hello, sir.
I don't think it works actually.
You are able
Hello.
to hear us?
Very faint actually. Hello.
Hello.
Come on again. Right now it is.
Sir, can you hear us?
Now is it clear?
Yeah, you can proceed, sir.
Okay. So as I was saying that this is mainframe. Mainframe is primarily consisting of rigid frames. Rigid frames are basically what? Rigid frames are basically tapered I section. Tapered is basically the web. The frame flanges are kept constant over the length. Okay, and plate thicknesses normally varies from 6 mm to 25 mm. If you say about say web, it starts from 6 and flange normally starts from 8. Okay, and normally we use 345 grade. And from end framing system, this is again, as I said, this is simply supported post and beam. Most of the times it is of constant depth, you can of say I, or you can have one single C or double C put back to back. So, and this is 345 grade again. Now for component also, the other important parts are in the secondary framing. Secondary framing consists of purlin, side cuts, and eave struts. Purlins normally we use Z purlins, right? And for C sections are also used as purlin and gut, but this is very rare. Normally C sections are used for some door jambs and few columns in the wall panel part. And this is called eave strut. Eave strut is a particular type of C section. It has some slopes on the, in the top flange as well as in the bottom flange. So, and this has got a very particular use. We will explain that particular thing in a subsequent slides. So these are normally hot rolled strips, and later on formed like this profile. So these are called cold form. So since this is forming, the basic formation is in the cold stage, this is called cold form. And for cold forming, there is a code that is IS 801. For design of such secondary framing, we need to consult IS 801. We'll come to that later on. And the thickness normally varies from 1.6 mm to 2.5 mm. Depending on the span of the purlin, that is the base spacing, right? So we normally use 345 grade. Sheeting and cladding, this is a very normal thing. Nowadays, you have seen a lot of trapezoidal color-coded sheets are available. Those things are used as sheeting and cladding. And base material is normally starts from the thickness of 0.47 mm and of 345 mm grade. Now bracings. So bracings is another wonderful thing over here. So in normal bracing, in normal structural bracing, we can use say angle, channel, or angle in a star formation. Many combinations can be done. But here in PEB, we normally use cables and or rods, simple rods as bracing. So when you design these particular bracings into STAT, it's STAT, and you have to model those things as tension only. Please remember. Okay, so you can have say 12 mm rods or 12 mm cables up to say 32 mm cable. You can use this. So as bracing both as roof bracings as well as column bracings. And fasteners for connecting primary frames, we normally use 8.8 grade bolts. And for secondary framing, that is for connecting C sections, Z sections, deep struts and all, we normally use 4.6 grade board. This is flashings. Flashings are basically secondary framing, but it is used as a connection tool for connecting the sheetings to the secondary frame. That is, secondary frames are purlins and guards. And when we attach the sheets to secondary frames, sometimes we need some further secondary framing that is called flashings. Here you can see this particular section is a flashing. Okay, and trims are normally taken from the sheeting material only. This is for connecting two sheeting material into one. Suppose this is an end frame and you will have a red trim over here. Similarly, in the ridge portion also when you join two sheet panels, and you have on the top of it, you might be having this thing or put a ridge trim over there on the top of it. Codes conformity coming to, and in the design, normally we use, as you know, we use IS 800 2007 for basic design of primary frames with hot roll sections and plates. This is for the rigid frames I'm talking about, and for the secondary frame, you need to consult IS 801. The present code is 1975, but as most of you would have already know that this particular code is under revision, and very shortly we can expect the new IS 801 would come. Otherwise, many people do what thing they may not be following this IS 800 for primary system and IS 801 for the secondary system. They simply follow the MBMA system, that is the American system, Metal Building System Manual, or we normally call it MBMA manual. There everything is there. I mean, people can also use that, and it is, I mean, many places it is also accepted. Now we are coming to loads. These are quite normal thing. You can see for dead loads, you have to consult to IS 875 part 1. For part 2 is used for live loads, and part 3 is used for wind loads. If you have this particular construction in a very seismic prone zone, you need to consult IS 1893. Although since these are very light frame structure, very rarely the seismic load will be guiding. Temperature loads, yes, sometimes we need to consider that. And in addition to that, if you have any collateral or ancillary load, I mean, because of the utility of the structure, you can consider this appropriately. But one point under this 875 part 2, when you consider the live loads, please keep in mind that in most of the cases, pre-engineered buildings are flatter than the conventional structures. So most of the times you will have the roof slope less than 10 degree. Okay. So if it is less than 10 degree, you won't have any liberty to reduce the live load as per IS 875 part 2. If it is more than 10 degree, you need to reduce the live load, but here there is no scope if the slope is less than 10 degree. Fine. Please remember that. These are some of the deflection limits. As this is again as per code. For rigid frame, for roof live load, you will have L by 250. So for horizontal loading, it is H by 60. Here also, suppose purlins, it is L by 150. These are considered for ductile sheeting, sheeting. And here in the floor beam, most of the times if we have the RCC slab over it, the brittle loading, so you will have L by 300 as the guiding deflection limit. Fine. So next we will move on to the support condition. As I said, please remember when we were explaining this particular thing, that is the frame optimization, what we said, that in the bottom at the support you need to consider as pinned base, right? So if that is so, then it is the duty of engineer, that is duty of the designer, or say after a few months it is duty of you how do you really, achieve those pinned bays over in actual condition? It is easier said than done. Then we can design the structure pinned base, and you can go on designing, and after completion of the design, you can have the drawings ready for installation. But really, in in the fire site, how do you really achieve this pinned base? Pinned base can be achieved, although it is not entirely achieved. Pinned base can be achieved if you put these anchor bolts within this space only. The moment you put the anchor bolts outside this column, it will give you eccentricity. And this moment, suppose here, so here if it is pull and push, then you will have moment over here. So that becomes a fixed base, right? So to achieve pin base, you have to put your anchor bolts as close as possible and within these two flanges only. So that is how we can nearly achieve this pinned base. So when your pre-engineered building is a normal thing and under the loads of dead load, wind load, normal collateral load, we can have your pre-engineered building pinned base and you can design like this. But suppose you have the, say, cranes running. So in that case, you have to consider the moment at the base, and in that case, it is advisable to go for fixed base and design your column as straight. Don't go for tapered. Design as straight and put the anchor bolt like this. Allow the moment to be here, and design the foundation, associated foundation accordingly. Design the foundation with moments only, moment and shear force. Here, the foundation would be designed only for the shear forces, so as the bolts. Fine. So here we will be discussing about some typical connections. Here you can see these are normal typical connections with columns and rafters. You can have 4 types of typical connection. One is like this. You can have your rafter sitting over the column. Okay. Here the rafter ends over here and fixes with the column at the face. Okay. Here, when the shear force is much more, you can design your rafter, detail your rafter like this. When the shear force is less, you can have detail your rafter or column connection like this. So at the same thing over here, only thing your rafter and column connects in a sloped line. Here also rafter connects with the column in a sloped thing. So these are 4 typical things, and here you can see this is a typical ridge connection, that is connection between rafter to rafter at the ridge. Here some intermediate splice. You can't have, suppose you have say 30 meters span. So in one rafter, you will have 15 meters. So 15 meter, a single member you can't have. So you might be going for say 2 7.5 meter part. So you need to have one splice design the splice. So these are typical splice design presented for your understanding. So this is typical design for if you have some internal columns. Most of the times we have say circular or square hollow sections as internal column. These are typical connection for that. Here also column to rafter connection. For bolt specification, as I said, the bolt class normally is used 8.8 here. From IS 800, if you can take the ultimate tensile stress of the bolt, you need to, for 8.8 class, you need to take 800 Newton per millimeter square as ultimate stress, tensile stress. And for yield, you will have, the nomenclature is fixed like that. That is 8 into 8, 64. That is the yield stress of the bolt would be 640 Newton per millimeter square. And for when you design the bolt for say tension, you have to go for core area. Core area is normally 78% of the gross area. Gross area is used for the calculation for shear. Okay, let's move on to this next slide. As I said, the whole concept of pre-engineered building is taken from your classroom. Here is another wonderful example how we design these purlins and guards. Suppose students, if you see, if you design instead a continuous frame like this, okay, continuous beam under dead load and weave load, what you will have in the last but one support, you will have the bending moment, this WL by 10. In the intermediate support, you will have WL by 12. And in between, that is in the mid span, you will have WL by 24. Fine. So you can see the bending moment here is minimum. In the support particular, Z section diagram, if you see, this top flange and bottom flange are not always equal. It is B1, it is B2. And if you see, these two dimensions are different. If B1 is 54 for a standard case, and B2 is 50. So this is done to allow for this particular lap. And in the last part one slide, this particular thing, here the lap is provided even more. For intermediate support, some lap is provided. For normal case, from center to this place is 300, from center to this place is 300. So total 600 mm lap is provided for a normal intermediate support. And for the last part one support, this is normally provided as 600, this side. And this side is 300. So this is how we take care of the extra bending moment coming over here. So I am sure you must have learned the designing of say continuous beam in your classroom. So this is a perfect example of how you can really implement your classroom teaching into this engineered building. Here also another insight. This is EBSTAT. We talked about EBSTAT, right? So this is EBSTAT. So for a normal bracing system, this is a normal bracing system. Now suppose if you put this particular say bracing as tension only, then there must be one member over here that should take your compression, because this member will take only because these are bracings or cable. This cannot take your compression. So there must be a member over here that to take care of your compression force. So that is this particular compression force is taken care of by the here in engineered building, the last purlin, and that is how we call it eave strut. It is placed in the eave, that is why eave and strut, because this particular member, although it acts like a purlin, but it primarily takes care of your compression force coming from this bracing system. So that is why we call it strut. So that is how this particular thing comes at eave strut. Okay. So, and this is the typical connection system of the bracing with the welding wave plate, right? This is a rod case and this is cable case. And little bit about STAD modeling. Most of you are very conversant with STAD, and some of you are more than conversant than me. So as you know, in STAD, when you detail this, you have to input the tapered property for tapered section, you have to provide. So since this is from in a STAD thing, you have to give the one part is deeper, another part is smaller. Wait. So here, depth of the section at the start node should always be higher. This is a limitation in STAD, and you should follow that. So at the start node, from your design geometry, please see what is your start node, and assign the member property like that. It start node always your higher depth should be there. Okay, and here the end node, the less depth will be. Otherwise, this is pretty simple. And welding issue. Later on when you join the prefabricated industry, you will see that in prefabricated industry, what they normally do is suppose this is your flange, this is your wave, and here there will be another flange will be there. They normally do one side fillet weld only, here and here also. No, say they do not weld over here. So this is done for the faster construction, and it is in this particular one side weld is enough. But only thing when when we design, we need to take care of the little bit eccentricity that is generated over here for the welding of one side, that you need to take care of that. Other side, normally they do stitch welding at a certain interval. And now we would like to move on to some few construction issues. And I will wrap up very quickly after this, because time is also constant over here. Anyway, so for foundation or anchor bolt, you need to check the rectangularity of this particular thing through diagonals, and say this is how we check, and the right angles are being maintained. And one thing, this is a standard, typical scenario for many of the cases. I have taken this picture from a practical site only. Don't leave, see here, they have, put the anchor bolts with the columns, but on the top of there is a gap, and they left it like that only. So never allow this type of gap to be there. Fill this particular gap with grouting, otherwise, extra tension will come onto these bolts. Okay, so there is need for filling this particular gap with grouting. Here, a little bit of storage. Storage should be always above the ground. It should be covered. Here, between these rigid frames, if you can put some wooden logs, it would be good. And if it is placed in a sloped condition, that would be another good thing. Then no, water accumulation would be there. And this is how we normally maintain the storage QAP in the site. Here, installation of rakers. Sometimes rakers are also called flange bases. You have the this thing in Z purling. You have the lap over here, but sometimes that is not also sufficient. So suppose your this thing spacing is more, so then you need to have another raker installed over here. This is the last slide. This is called sheeting and cladding, and you will have for sheeting, these are the normal stitch screws or self-tapping screws, and this is how we should proceed. Suppose here in the normal case, suppose first you have to install the last panel over first. The last panel you have to install first, then go onwards like this. This is 1, 2, 3. Again, this is 1, 2, 3, and 4, 5, 6. This is how you should go on and lapping, so that there is no scope for any leakage. And if there are some skylights to be installed in the thing, in the roof, so it would be installed later on. This is the 7, and this is how your stitch bolts is required for connecting sheet to sheet, and these self-tapping screws are required for connecting sheet to purling. Okay. So I believe I have covered a lot of things regarding design and construction of pre-engineered buildings. But as I said in the beginning, this is a very established industry. A lot of improvements have been there. So you will have many literature in the internet for your understanding. And of course, if you need any further guidance, please do write to us. And now I open the floor for questioning. Dear students, if you have any question, you can ask. You can write to us later on also. We are always open. So please do whatever you feel convenient to you. Sir, if you have any question, or if you students have any question, please carry on. Thank you.
Thank you, sir, for that wonderful information. Sir, I have few queries.
Sure, sir.
I have few queries. Usually, you said that they will be designing using MBMA code and IS 800 code. So which one we have to exactly use in the Indian scenario, and which is much economical?
Sir, first of all, as I said, both are used. This is number one.
Mm-hmm.
Number two is, as far as conventional engineering practice goes, one should use only one type of code. I mean, it should not be, I mean, for some you use IS 800 and for some component you use MBMA. It should not be like that. I mean, for a single project, you should, I mean, one should follow only one standard, either MBMA or Indian standard. Now, sir, Indian standard, in Indian standard, there is some issues. And why people normally use MBMA, I'm telling you, sir. In IS 800, IS 800 does not allow design of slender sections. IS 800 normally allows for design of plastic, compact and semi-compact sections. But MBMA does allow design of slender sections also. But there is a rider, you have to reduce the effective area correspondingly. Okay. So that is one, and you know, sir, in engineered buildings, thinner sections are used. Even a thickness of 5 mm is also used as frame, right? So
Yes,
that is one reason people do prefer this thing, MBMA. And deflections criteria also, in such cases, deflection criteria in IS code are normally stricter than MBMA. Okay. And in another major thing is load. I can give you one example that I was talking about IS 875 part 2. And since we have, in most of the cases, pre-engineered buildings, the slopes are less than 10 degree, you cannot allow for any load reduction, live load reduction at the roof, even for inaccessible roof. Okay. And for some, for say IS 800, 875, the load is 75 kg per square meter. But if you refer MBMA, you can have 57 kg per square meter. So there is a reduction. So in live load case only, there is a reduction of this much, 75 in IS code, 57 is MBA code. So by following MBMA, people have lot of, I mean, economy. And nowadays, since this Indian case, IS 800 is one. For that, I mean, for rigid frames, you need to consult IS 800. 801 is still under revision. So these are these sort of, I mean, inconveniences. People normally prefer, even the clients also, they prefer MBMA because under one roof you will get everything. So, and the contractor side, if they follow MBMA, they can achieve economies. And in the age of cutthroat business, it makes sense to go for MBMA.
because whenever we design the structure, and if it goes to third party for scrutiny, they say they do not allow us to go for using this MBMA code because of since it is Indian scenario, they say you should use 800 code only.
But in that case, sir, you have to go for, I mean, for rigid frame design, you have to refer to IS 800. Okay. And for secondary framing, that is Berlin and struts, you have to go for IS 801, which is, I mean, a very dated code actually.
Sir, we designed this rafter and this column based on the bending moment diagram, and how to limit the depth of the beam at let us say this point of counterflexure.
Okay.
There is the bending moment is 0.
Yes.
But minimum depth is how much is the minimum depth we should provide at that point?
Sir, normally, as far as I mean, my knowledge goes, or whatever structure I have designed, normally I restrict to say 250. I don't go below 250 or 275.
How much, sir? Can you pardon me, sir?
275 is the overall depth. Say 250 is 250, around 250 is the wave depth.
Okay. 75. Okay, sir. So then, is the fixed base foot foundation is better, or considering in this TAD, is the fixity condition is better or hinge condition is better? For
hinge condition is better when you don't have any crane loads and all. But if you have crane loads, you must be providing the fixed load. Fixed based scenario. Okay, but for normal cases, that is dead load, live load, wind load, and say, some amount of collateral or ancillary load, you can go for pin base.
Okay. Okay, sir. But even if we use this fixed case, the foundation sizes will be
More.
normally
Yes,
on
more,
their
because
side.
I mean, you are allowing moment to be there.
Yeah. Sir, another question is for this rafter, we have this effective length condition. Since we provide
Effective length
purlin,
condition, right?
does the effective length changes because the purlins, though they are lateral members for this beam, they are very thin members. Can we still take the effective length as the distance between the purlins, or is that we need to take it for the entire length of the beam?
Because your bottom flange is not restrained. But for or say 1400, whatever your purlin spacings are.
Okay. Sir. And sir, is the racker a must?
No, sir.
To
Rackers or flange base are not must. I mean, for say, I have not used that, sir, for say 6 meter, 6.7, up to 7.5 meter. I have not used. But if it is more than that, sometimes we need to use that.
And this regarding this tie beams we provide between the columns and for the rafters, is that we have to provide for the first bay, or usually what is the condition, sir? Is it must?
That is, you are talking about the bracing system, right?
Yes, sir. Bracing system, sir.
Sir, it is always better if, I mean, for a standard length, I am saying, it is always better if we can put the bracing system in between, in the central bay.
Okay.
But sometimes
center and last
longer, then we have to put in the central bay and those, I mean, end bay also, two end panels also.
So starting, middle, and end. That is what you suggested, sir.
Yes. But for a standard thing, say up to say 50-60 meter length, is always better if you can put the bracing in the central.
Okay. And regarding this hillside washer,
sir,
can we provide the regular bolt, or is it a must to provide the hillside to use hillside washers?
Sir, in the regular thing, I mean, hillside washer is better because that fits better. I mean, in the regular bolt, since your bracing is intersecting the this thing flange in a, in an angled way actually, right? So your normal nuts may not fit tightly. So hillside, with the provision of a hillside washer, you can have a snug tight condition over there.
Okay. Sir, another small last question. So, do you recommend while modeling in STAD, do you recommend the plane frame analysis or the 3D?
Yes, sir. I always, sir, this is my view. Entirely my view, sir. I have seen many people, modeling the whole PEB in the STAD. But as I said, PEB incorporates classroom to type teaching. Normally what we learned in the classroom, and in the classroom we have learned that this type of two-dimensional frames are basically, these are basically two-dimensional frames, right? So two-dimensional frames are always better if you design as plane frames. And for the loads from the other side, that is the third direction Z, you can always design that particular bracing system separately.
Okay.
There's a moment in space. It is basically you are allowing a space frame design to take place.
Yes, sir. Which you said is that we need to model a separate.
I design it
model for that.
Yeah, I design it separately, or even if it's not a model, I can do it by say hand calculation also for bracing. It is simple. Calculate the roof drag, calculate the wall drag, and distribute in two sides and just design this particular bracing system.
Okay, sir. Okay. So thank you so much. I have finished my questions. Anybody else, if they have any questions, please.
Can I stop sharing?
Yes, sir. Yes, sir.
Hello.
Anybody else, if they have any questions?
Hello.
Yeah,
Hello,
Chandan, I
sir.
can speak. Yeah.
Sir, can you hear me, sir? Frame
For
sections or
whole of
PEB. Hello.
PEB as a whole.
You can use for both.
Hello. Sir, MBMA is only for cold frame sections or PEBs?
Sure, ma'am. As in the previous
These
section,
are the questions.
Mr. Samant
And if
also
there are any
requested
other
you
questions, we
to
can
please do write to us for
send
any
you.
queries.
So,
We will be very
further
happy
send you by
to address your queries. Please feel free to do so, sir and madam. So,
Yes, sir.
Okay, sir.
okay. And we will have a lot of other sessions in the subsequent, days also.
Yes,
So
sir.
please ask you to have, freely ask questions. There is no silly questions, as you know. Yeah? So please ask them, ask questions.
Yes, sir.
Please encourage them to ask questions.
Definitely, sir. You are so generous in that way. Thank you so much, sir.
Thanks a lot, students.
Thank you so much.
Okay, sir.
Yes, sir. We can end this session, I think. Thank you so much.
Okay, thank you everyone for attending the webinar, and here is signing off and ending the webinar.
Thank you so much, sir, madam.
Thank you. Thank you.
Sir, should we log out?